Okay, so we're going to continue our next lesson here on connectivity with a couple of very meaningful theorems that kind of either give us a nice structure that we'd like in a graph or an obvious reason why it can't exist. Of course, we like these theorems a lot. A theorem like Tut's perfect matching theorem. Either you have this wonderful thing, a perfect matching, or there's some structural reason why not. Those are really powerful tools that give us a lot of useful information about graphs. And we have several of those coming in our connectivity settings here. And and as I think I'd indicated before, this is part of the reason why graph connectivity is such an important property. It's not only that it's a natural and meaningful property of a graph, but it's also that we have some very important structural things to say about it. And we're going to see kind of a first instance of that right here. Um, also, I think, as I indicated before, I'm not really taking the most efficient line toward these proofs. I'm trying to do something that's a little bit instructive and getting us to kind of play with some of these parameters. When it comes time to really prove the whole big theorem, we will do it as efficiently as possible. But that's just not my concern for right now. So I do want to step back and just remind you what a separation is once more, because that's going to be key in everything we're doing today. So again, when I think about a separation, I am drawing myself a picture. I am thinking about taking a graph and putting it into two bags. There will be a bag on the left and a bag on the right. And how does this work? Well, there are going to be some vertices here that are allowed to be, that are in the middle. They're in both the graph on the left and on the right. And the rest of your graph has to then fall down into these bags. So what does it mean? Well, it means you can add some vertices in these bags. Sorry if I'm not drawing particularly exciting graphs here, but so be it. You can add some vertices in these graphs and into these bags, and you can add some edges. And now what's going on? Well, so again, I've split the graph into, there's a bag on the left, there's a bag on the right, and it's giving us some kind of simple structure in our graph. Now, when we go to actually formalize this, we've introduce this notion of a separation. So the separation is going to be given by this pair of subgraphs, H1 and H2, and that's the bag on the left and the bag on the right. And the rules are that, well, the union of those two should be the whole graph. You're not allowed to have an edge in both. So for any edge, it has to be either in the left bag or in the right bag. And if you have a separation of order k, that means you're going to have k vertices shared between the two bags. And I'll remind you, we've seen a couple of nice observations already. For instance, a graph is disconnected if and only if there's a proper separation of order 0. Oh, I remind you here again that proper means there's a vertex on the left but not right, and one on the right but not on the left. Okay, so let me just jump. Let me hope you have this in your head. We are going to be proving a very natural proposition that gives us one of these nice if and only if theorems about graphs. Either we're going to have a nice thing that we'd like, or there's going to be a good structural reason why not. And it's going to involve a pair of edges. So what we're going to do is I'm just going to give you two edges in a graph E and F, and I'm going to ask, is there a cycle that contains both E and F? Of course, if I gave you just one edge, E, you know there's a cycle containing E if and only if E is not a cut edge. That's down to basic connectivity. But now that I've added a second edge, well, things have got a lot more involved. When is there a cycle between a pair of edges? And what we're going to prove is a nice proposition telling us either you get it, either you get this thing that you'd like, or there's a good structural reason why not. And that structural reason why not is going to come in the form of a low order separation. So let's state the theorem. I call it a proposition in the notes. So E and F are distinct edges of G. And then exactly one of the following holds. So either there's a cycle containing both E and F, or the other thing, why wouldn't there be a cycle? So why would there be no cycle containing E and F? The other thing that could happen is the obstruction. The thing that prevents that is the presence of a low order separation where you have E on the left and F on the right. So the other possibility is that there is a separation H1 comma H2 of order less than or equal to 1 with E an edge of H1. Whoa, what am I writing there? And F an edge of E2. F an edge of H2. So let's see why you can't have both. Suppose you have this structure. You have a separation of order at most 1 with E on the left and F on the right. So I'll draw it of order 1 because that's maybe a little bit more natural or more the more interesting case, I suppose. So there we are. There's some separation of order 1. I don't know. There's some graph on the left. Actually, let me ignore the graph on the left. Let me just draw a separation of order 1. Somewhere over here is E, and here over here is F. It's possible that F is incident with that vertex in the middle, and same with E. But I'm claiming that as soon as you have this property, you cannot possibly have a cycle that contains E and F. And why is that? Well, let's suppose you have a cycle that contains E and F. Remember, E and F are not loops, right? I'm assuming that I'm operating with loopless graphs at the moment. So if I give you E and F and these two edges they're not loop edges. If you do have a cycle, well, let's take that cycle and just delete the edges E and F. Then you have two completely vertex disjoint paths that go from the two ends of E to the two ends of F. Well, that can't possibly be if you've got a one separation here, right? If you were going to have that structure and I showed you a separation with E on the left and F on the right, well, then you'd have to have two vertex disjoint paths that go from the left to the right. But that just can't be happening here because this vertex in our one separation, the unique vertex in the middle there, would have to appear on any path that starts at an end of E and ends on an end of F, because E is on the left and F is on the right. So what we've just done is, well, I've drawn the picture associated with our second property here, but we've also kind of, in doing so, already argued that these two conditions, 1 and 2, are mutually exclusive. You can't have both a cycle containing E and F and also a separation of order 1 or order 0 with E on the left and F on the right. Yeah, this just gets a little bit more ridiculous if it was a separation of order 0. Okay. So that's our target to prove. And we've proved that these things are mutually exclusive. And we are going to now prove that at least one of them holds true. So it's going to suffice for our argument to show that one of these two properties is true. Now, let me note, we may as well assume that the graph G is connected. If the graph G is not connected, then there are two possibilities. Either E and F are in the same connected component or they're indifferent. Well, if E and F are in different connected components of the graph, then you have a 0 separation with E on the left and F on the right, right? You can take the connected component containing E as your graph on the left. You can take all the rest of the components on the right-hand side, and that will be the desired zero separation now with E on the left and F on the right. So if E and F were in different connected components, then we're done. Then we already have that second outcome. So I can assume that E and F are in the same connected component. But then suppose E and F are in the same connected component and there's another connected component over here. Well, you may as well just delete that connected component. It's not going to change the outcome at all. If you have a, so suppose you remove this connected component. If you were now to find a cycle containing E and F, then sure, that existed originally. If you had a one separation, say, with E on the left and F on the right, and you just removed a connected component, you could add that connected component back to either side of the separation, and you'd still have a one separation separating E and F, with E on the left and F on the right. So maybe I said that a little bit quickly, but this is a thing that you can very readily verify for yourself. I'm just going to say we, WMA, we may assume that G is connected. And again, the argument here is, well, if G is disconnected, either E and F are in different components, and then we have the second outcome, or they're in the same component, and in that case, I can just simplify the picture by deleting the other another connected component. So so if you, in other words, if you know how to solve this problem for connected graphs, you also know how to solve it in general. Okay, so we're safe to assume that the graph is connected, and now we're going to play a bit of a funny game. We're going to do induction on a somewhat unusual parameter. I am going to take my connected graph. I've got an edge E and an edge F. Well, if you've got a connected graph containing the edges E and F, you have a walk that contains both E and F. And so there's a shortest walk containing E and F. If you think about a shortest walk containing E and F, you know, the edges E and F had better be the first and the last edges of this walk. I mean, if the first edge of the walk is not one of E or F, you might as well just delete it and you have a shorter walk that still contains E and F. So if I take a shortest walk containing E and F, then, excuse me, if I take a shortest walk containing E and F, then I can assume that, say, E is the first edge and F is the last edge. That's what we're going to be operating with. Now, how are we going to do an induction? I'm actually going to do induction on the length of that walk. So this is a bit of a crazy game, but it's what we're going to do. So I'm going to let K be the length of the shortest walk containing E and F. There we are. So K is that length. Now in this case, of course, if you're E and F are, I should have said E and F are distinct edges. I hope it says that in the notes. Yes, it does, yeah. So I'm giving you two distinct edges, E and F. And now I want a walk that contains those two. Well, it's got to contain the edge E and it's got to contain the edge F. That means the walk has at least two edges. So the shortest the walk could possibly be is length 2. So I said I'm going to be, so K is the length of that shortest walk. So K can be 2 or 3 or 4. Now the funny thing we're going to do is we're actually going to go by induction on K. So we're going to go by induction on K. This may seem a bit of a funny thing to do, and yeah, it's I think there's one of these choices that after you see the argument you'll realize why it was a good idea and how it sort of gives you something useful. So I think it's maybe best to just let this one play out. But let me just note here that it's perfectly valid, right? I'm allowed to do, I mean, give me any parameter in a graph as long as it's taking, say, integer values and bottoms out somewhere, I can try going inductively on that parameter, right? You're talking about pairs of edges, E and F, and we're going to look at this parameter, which is the length of the shortest walk containing them, and we'll go by induction on that parameter, right? Where it's perfectly valid. We're always allowed to do that. This is an integer parameter. It bottoms out at 2. We can go by induction. If we want to do that, we're going to have to handle the base case and the inductive step. And if we can succeed with these, then we win. Then we're done. So k equals 2. So if k equals 2, then E and F actually have to share an endpoint, right? Then I can assume that I may as well assume that E equals, say, UV, and F is the edge from V to W. So this is just some of the usual shorthand here. U and V and W are vertices. E is an edge with ends U and V. F is an edge with ends V and W. If E and F are parallel, then you're done. Then you already have a cycle that contains both of them. So you may as well assume that E and F are actually not parallel, that they're that these vertices U and W are actually distinct, right? So let me draw a picture. So in this case, when k equals 2, here's my edge E. It goes from U to V. And here's my edge F. It goes from V to W. And here, if you're hoping to make a cycle in your graph that's going to contain the edges E and F, it's pretty clear what you need to do, right? What are you going to need if you want a cycle that contains those edges E and F? Well, you're going to, at some point, you're going to have to, when I walk around your cycle, you're going to have to come to the vertex U, go through the edge E to V, then through the edge F to W, and then back around to U, right? What you need to find is this part, right? And what is that part? Well, that part has got to be a path from the vertex U to the vertex W, but is not allowed to use the vertex V. Right? It's no fair stepping on V in the meanwhile, right? So the key feature here is that because U and V actually share this common, because E and F share the common vertex V, your graph is going to have a cycle containing E and F if and only if there's a path from U to W in G delete V. So G has a cycle using E and F if and only if, let me put that over here. I'll just write if and only if G minus V has a path from U to W. Okay, well, I know when a graph has a path from U to W, a graph has a path from U to W if and only if U and W are in the same connected component, right? So what's going to happen here is, well, if G delete V does not have a path from U to W, that means that U and W are in, so let's do both sides here. So maybe let me draw more pictures. So suppose there's no path from U to W in G delete V. Let's draw that. Well, so sorry, let me keep track of what I need to do. We have a cycle using E and F if and only if G delete V has a path from U to W. So if there's a path from U to W in G delete V, then we've got our cycle using E and F, and we've got the first outcome, and we're done. So in other words, what I need to do is the case I need to handle is what if I don't have that? So what if U and W are in distinct components of G delete V? that's the picture I'm going to draw. So here's the vertex U, and here's the vertex W. And now U and W are in distinct components of G delete V. And now I'm going to do the thing that you saw me do in the previous lecture, where we're going to take this graph and we're going to take G delete V, and we're going to extend to a 1 separation in the original graph. So as usual, I mean, so I'm supposing here that G delete V, the only remaining case here is G delete V. Let's say if U, W in distinct components of G minus V, then here we are. Right now I'm going to draw G minus V, and maybe I'll have to erase this part up here for now. So here's the graph G delete V. U and W are in distinct components of this thing. Now what I'm going to do is I'm going to go from G delete V back up to the original graph G. I'm going to add back the vertex V and its incident edges. So here it is. There's the vertex V. And where its incident edges, well, my original graph was connected, so it has to have some like so. And now I'm going to show you a 1 separation in the original graph. Where's my 1 separation? It's right here. So again, I think of a 1 separation as a pair of bags. So what I've done is I've taken my, after removing the vertex V, U and W are in distinct components of G delete V. So I'll line up all the components of G delete V. Maybe I'll take, I'll take those components, and now I'm adding the vertex V back. So V gets added back and together with its incident edges. And now I'm going to form a 1 separation, and I'm just saying in words and pictures how we do this. It takes a little bit of writing to sort of say all the things we're going to do, but if you understand the argument and get accustomed to it, the writing part, it just takes a little sophistication. We have U and W in separate components of G delete V. I'm now returning from G delete V to the original graph. I'm adding back the vertex V and its incident edges. I'm now going to form a 1 separation by taking that as my left-hand graph. I'm going to take the component containing U together with the vertex V and all the edges in between. And then that'll be my left-hand side, and then my right-hand side will be all the rest of the connected components. And you can see the key feature here, which I better highlight for you. Of course, UV is an edge of our graph. Here's UV. VW is another edge of our graph. UV was the edge E, VW was the edge F. So when I have done this, I have constructed, we have discovered a 1 separation in our graph that has E on the left and F on the right. And that was our second outcome, right? That's what we're aiming for. So what we've done here is we've shown that if you have 2 edges, E and F, that share a common vertex, then either there's a cycle containing them both, or there's going to be a 1 separation with E on the left and F on the right. And that's what we were aiming to prove. So now we've completed the base case. So we had to work a little in the base case here. It's kind of nice to do every once in a while. So now next up is the inductive step. So for the inductive step, now I'm in a sort of funny place. So I have this shortest walk from E to F. I can maybe draw it. There's E. There's F. Maybe this is W. This is our shortest walk from from E to F. And what we're going to do here is, well, I said we're going by induction. If I want to go by induction, the point of that should be taking advantage of the inductive hypothesis. And it sounds like a funny thing to do here, but it's actually quite useful. So let's think. So for the inductive step, I'm going to have the shortest path, shortest walk containing both the edges E and F, And here K is going to be at least 3. So that means that, well, E is going to be the first edge of the walk and F is the last without any loss of generality. And the length of this walk is at least 3, so there are some other edges. And what we're going to do is we're going to just look at the edge that's next to F in this walk. There it is, F prime. So what's going on? So again, W is just going to be a shortest walk that contains E and F. That walk is going to have length K. Now, if I take the edge just before F on this walk, let's call it F prime, now there's a walk from E to F prime of length K minus 1. So that's good because it allows us to apply induction. Now, this might not be the most natural sort of line you could think of, but it's certainly perfectly valid, right? We're going by induction on K. If you see any two edges that are contained in a walk with length smaller than K, our induction hypothesis works, or our theorem will tell us by induction for those two edges that you're looking at, either there's a cycle containing both, or there's this reason why not, this good reason why not. There's a separation of order at most 1 with 1 on the left and 1 on the right. And that's what we're going to be applying here. So I'm going to, let me, this is written out in the notes. I'll make sure I align my, my letters with the notes. So in the notes, F is the edge UV and F prime is VW. Okay, so there we are. So there's my walk. My W again is meant to be a shortest walk containing E and F, so without loss, E is the first edge and F is the last. F prime is the penultimate edge, the second to last edge of this walk. And I'm assuming here that F uses the vertices V and U, and F prime uses V and W. And I'll remind you that there are no loops in this graph, so F and F prime are not loops. And moreover, U and W are going to have to be distinct. Otherwise, I mean, if F and F prime were parallel, then you could have just put F in place of F prime and had a shorter walk between E and F. So those three vertices, U and V and W, they will really be pairwise distinct. And we can apply induction, so let's just do it. And this is one of these theorems where the induction, a cycle containing E and F prime isn't exactly a cycle containing E and F. It's a little different, but it's a useful structure for us to start from. And a 1 separation separating E and F prime, well, it's not necessarily a 1 separation separating E and F, but it's close. So the structure that we're going to get here when we apply induction, it's not quite the thing we're aiming at, but it's in both cases going to be pretty close, and then we're going to be able to take advantage of that structure to complete the proof. So that's so that's how this goes. So there we are. Now, as I said, there are two cases. We've now got E and F prime. When we go to apply our theorem inductively with the edges E and F prime, we're going to get one of two things. So by induction, E and F prime, they either satisfy property 1 or property 2. So I guess I clicked twice. So they're either going to satisfy property 1, there's going to be a cycle containing both, or they'll satisfy property 2, there's going to be a separation of order, at most 1 separating them. I'll remind you, we're assuming now that G is connected, right? I can assume G is connected without loss. So in fact, if you had a separation with E on the left and F on the right, the only possibility, if separation of order, you cannot have a separation of order 0 with E on the left and F on the right because the graph is connected. Okay, so by induction, E and F satisfy either 1 or 2. And those are just going to be two separate cases for me. Let's do. Maybe this is not the way it's done in notes. I don't. It doesn't matter. Let me. I've got my notation the same as the notes. So I'll do case 2 first. Two is actually the easy case. Suppose I had case 2, and I'm gonna lean on the notes here a little and mostly focus right now on kind of drawing the picture. Suppose 2. So what does this look like if you have case 2? That means there is going to be a 1 separation of the graph. Let me draw it like this, actually. So that means our graph is going to have a 1 separation here with the feature that E is over here on the left and F prime is over here on the right. Now, so this is, again, again, the writing here is in the notes. I'm going to try and say the right words and focus on the picture a little bit more. But by induction, I'm considering the case here that, so in case 2, what I get is I have a 1 separation with E an edge of H1 and F prime an edge of H2. Right? So this is one of the outcomes that my my inductive application of my theorem can give me, right? When I take the edges E and F prime, they're closer together than the edges E and F. That means inductively the theorem holds true. That means either I get outcome 1 or outcome 2. Either I get a cycle containing E and F prime, or there's an obvious obstruction. There's a 1 separation with E on the left and F prime on the right, rather. And I'm handling that latter case first. So now I'm looking at this 1 separation. E is over there on the left. F prime is over there on the right. Well, let's think about the edge F. Of course, you know, the thing I really care about, I really care about the edges E and F. I'm trying to determine if there's a cycle that contains the edges E and F, or if there's, I'm trying to show that either there's a cycle containing E and F, or there's a 1 separation that separates them with E on the left and F on the right. So let's ask about the edge F. Where's the edge F? Well, I mean, I've got a 1 separation. F has got to be on the left or on the right. Suppose F is on the right. Suppose F is over here. Oh, then we're done. Then we have outcome 2, right? If the edge F was an edge of H2, then 2 holds for G. And that means we'd be done, right? If I put F over there on the right-hand side, then I found a 1 separation in my original graph. E is on the left, F is on the right. That's what I wanted. So I can assume that's not actually the case. So this is not the tricky case for me. F has to be, in fact, over here. But now you see something funny. Well, F is on the left and F prime is on the right, but F and F prime have a common endpoint, right? The vertex V is common to them both. So, well, this can happen, but it can happen only one way, and it's not quite what I drew here. The only way this can happen is if F looks like this and F prime looks like that. So this would be the vertex W. This would be the vertex W, and this would be the vertex U over here. Okay, so, well, as I say, this can happen, but the picture had better look like that. And, well, if it does look like that, then we haven't succeeded, right? I mean, we found a 1 separation separating E and F prime, but not a 1 separation separating E and F. And so this might sound like bad news, but here there's another contradiction that we can get. What is that? This might be a good time to pause and think. You think, what's wrong with this picture? Why are we not going to see this configuration? So let me give you a moment to pause the video and think about that. Okay, so if you figured it out, congratulations. If you're just kind of listening along, the issue here is that we chose a shortest walk from E to F, right? That walk W was the shortest walk from E to F. What is that walk doing going all the way over to the right-hand side of this one separation, right? Let's think about what that walk W must look like. Well, it starts at E, it goes along. At some point, that walk is going to come to the edge F prime, but when it comes to the edge F prime, it has to have an edge using this vertex V. But the next edge could have used F instead of F prime, right? So at the point in time where you first visited the edge F prime, you must have, when you first visit the vertex V, instead of using the edge F prime, you should just use the edge F. That would give you a shorter walk from E to F. So if F is an edge of H1, well, then that's just silly. Then what you should have done is, then there's a shorter walk from E to F that does not use the edge F prime. In fact, what you can do is you can just follow along your walk till you first come to the vertex V, and then just add the edge F. And that's a contradiction, right? I mean, again, K is, I mean, we're operating with a shortest walk from E to F. Its length is K. If you are running along your operations and you suddenly find a shorter walk from E to F, well, that's a contradiction. That means this could not possibly happen. So in fact, what's going on here is if you did find a one separation with E on the left and F prime on the right, the only possibility is that F is also on the right, and that means we get the one separation. So that's a win. So yeah, I'm not going to write all of these things. I'm sort of writing a spattering of the argument here. These arguments, the pictures and the comprehension are vital. The ability to write the words, I mean, I don't want to downplay it. I mean, it takes some sophistication to go from seeing the picture to writing the argument, but it is just that. It's a little bit of sophistication. And yeah, anyway, I think I'm doing the best I can here by providing you the notes and then just doing what I'm doing here. So that was our first case. So again, we are proceeding inductively on the length of the shortest path that contains E and F. We did a base case where E and F are in some walk of length 2. We're now proceeding inductively, and what we've done is instead of going from E to F, we're now thinking about the second to last edge, and we're calling it F prime. So E and F prime, those are two edges that are contained in a shorter walk. They're contained in a walk of length K minus 1. And that means that we can apply induction to E and F prime. Again, there are two cases. Either we're going to get a one separation separating E and F prime, or we're going to get a cycle containing E and F prime. So let's consider that next case. So the next case here, case 1, is there is a cycle using E and F prime. I mean, I can be a little bit more proper. Okay, and let's draw this picture. So, other possibility here, and the other interesting possibility is that we found some kind of cycle here, and there are two important edges for us. One of them is over here is E, the other one is over here, it is at F prime. And, well, of course, the edge F is also vitally important, but E and F prime are what we know about. There's a cycle containing, E and F, sorry, that's F prime. So let's draw that guy. So there's E and there's F prime. Again, F prime is the edge from W to V. And the edge F has ends V and, excuse me, the edge F has ends V and U. So let's think about what the edge F might look like. Again, when you're thinking about proofs by induction. You're proceeding by induction on some parameter. You're trying to prove something. The thing you know is that your property holds in all smaller instances, whatever that could be. We've got a smaller instance. It gives us this cycle. Now, this cycle is not what we want in the original. I mean, I want a cycle using E and F, not a cycle using E and F prime. But that's okay. I've got some value out of applying induction. I've got a structure. We see a cycle, and moreover, that cycle we know something about where F lives relative to this cycle. So this induction. It's not that we just go apply induction and carry our bags and go home. No, this inductive application, it's given us some graph structure, and we're going to try to take advantage of that to prove what we want to prove. So where's the edge F prime? Where's the edge F? Well, there are kind of two possibilities. Either the vertex U, which is the other endpoint of F, one endpoint is right here, right? This vertex V, that's excuse me. The vertex V is one end of the edge F. Where's the other end of F? Well, there are two possibilities. Either it's on this cycle or not. And you can pretty easily see if I draw it on this cycle, like so, for instance. Oops. If this is the edge F, well, good news. There's a cycle containing E and F, right? We just when we go around this cycle, instead of using this lower part of the blue cycle, you just shortcut along that edge F, and hooray, you found a cycle using E and F. And similarly, it might look a little bit different, but the argument's just the same. If you draw your edge F like this, the same thing. Your graph is going to have a cycle that contains E and F. Here you just throw out the kind of upper right portion of that blue cycle and you shortcut. You shortcut it along the edge F, and that gives you a cycle. And so let me actually say that I'm being a little bit more. Some of these cases can be very efficiently wrapped up without singling them out, but I feel like it's easier maybe just to take a moment and talk this through just so you see how things work. I think in the write-up I'm maybe being a little bit more efficient, but I'll just comment, if the vertex U is in V of C, then in fact there is a cycle containing E and F, and we're done. And that means that case 1 holds for my original graph and the edges E and F. So by 1 holds for E and F, I just mean that there's a cycle containing E and F. Okay, so that's not what's going to happen here. That's not where our edge F is going to go. And it means that our edge F has to kind of stick out and go to a new vertex. And again here, well, okay, now what's going on? I was supposed to try to find a cycle containing E and F, or this one separation, and I'm not getting either of those things here. But we have something, right? Our induction has brought us something. We've got a picture. We've got some graph structure. So let's try to lean on that. Let's try to see what we can see. Now, maybe once more, I'll say, if you want to pause and think how you would proceed from here, it's probably a good thing to try. So if you want to just pause the video for a moment and think what you would do next. How am I going to try to either find a cycle using E and F or find a 1 separation? And I'll give you just a sec to pause the video. Okay, so if you saw it, congrats, and if you're just listening along, no problem. The thing we're going to do here is we're going to consider deleting V, right? Our vertex F, our edge F has ends V and U. And we can mimic that argument that we just saw. We were just considering the possibility that U lies on the cycle. But in fact, we can get a similar case. Suppose I could find a path that starts at U and comes around to the cycle not landing on the vertex V. Right, so I don't want this path to ever use the vertex V. No touching V. But it's supposed to start at U and it's going to go around, and I'm going to stop the path as soon as it touches a vertex of the cycle. So I'm really giving you a little orange path like I've drawn. Well, in this case, you are going to be able to find your cycle containing E and F. You can see how to route it here. I can't really gesture very conveniently, but if you just drop out this, you kind of have a sort of a theta picture like this. If you drop out this middle vertical line in your theta, you're going to be left with a cycle that uses both E and F. So we're going to basically try to get this, and that's going to once again break us into two cases. So if there is a path, oh, sorry, let me even just back up and let's just consider the graph G minus V. G minus V. Now, G minus V might be connected and it might be not connected. But I do know some things. Namely, if you take that whole cycle C and delete V from it, that's all going to be in the same connected component. So if C minus V and the vertex U, if those are in the same, actually, let me do the opposite case first, because I think it's maybe a little easier. If C delete V and U in the different components of G minus V, then what does that look like? I'm going to do the same thing you've seen me do a couple times already. So let's say these are the components of G delete V. Well, that cycle C delete V is over here. Maybe this is, here's C minus V, and maybe the vertex U is over here, and maybe they've got a couple other components. So that's what G delete V looks like. Now what am I going to do? I'm going to put the vertex V back. Where does it go? It goes up here. There's the vertex V. Of course, my graph is connected, so V is going to have some edges down. In fact, I know that the vertex V is going to have an edge to this guy and this guy, because C is a cycle, right? C delete V, when you add the vertex V back, you get the edges between that vertex V and the two ends of the path C delete V. So there we are. There's some of my graph. And I also know that VU is an edge, because that's the edge F. And V will have to have edges to any other connected component of G delete V, because again, I'm assuming the graph is connected. But this is my picture. So if C delete V and U are in different components of G delete V, what am I going to have? This is the same argument that we saw before. Well, after deleting V, I've got these connected components. That's going to give me a one separation where V is the middle vertex in the original graph. What do? I'll just draw the bags for you. And as usual, this argument is, this is all done clearly in the notes. All of the words are here in full in the notes. I'm going to give you a subgraph H1 and a subgraph H2, and what I'm going to do is just what I'm drawing. Again, if C delete V and the vertex U are in different components of the graph G delete V, then what I will do is I'll take the connected component of G delete V containing C delete V, containing all the rest of that cycle, and I'll add to that the vertex V and all edges from that connected component between that connected component and V. And that's going to be my left-hand graph H1. For H2, I'll take all the rest of the connected components of G delete V. I'll add back the vertex V and all the edges, all those missing edges between V and those other those components. And that's going to be what I declare my subgraph H2 to be. And if you've done this, then in fact you're winning. Then in fact the you can see my whole cycle. Sorry, this picture's getting a little bit messy. But my whole cycle C is over here. And the edge E lies on that cycle somewhere. So the edge E is there. The edge F, that was right here. So we've found a 1 separation where E is on the left-hand side and F is on the right-hand side. So that's outcome number 2. We've found outcome number 2. So if C delete V and U were in different components of G delete V, then we win. Then the argument is just what I've drawn here. Again, what I'm hoping you'll get comfortable with is thinking in terms of these separations. We're taking little bags of graph and kind of drawing pictures and learning to operate with them. It takes a little bit of thinking to kind of wrap your head around this definition, but once you get it in your head, it's really very natural to kind of draw the right picture and then hopefully to kind of write the right words as well. Okay, so we've done one of the 2 cases. If C delete V and U are in the different components, then we win. The other possibility is C delete V and U are in the same components. And in that case, what does that mean? That means that you can choose a path so I'm giving you C delete V and I'm giving you U. Well, if they're in the same component, that means you can choose a path that starts at the vertex U and connects to, in fact, any vertex of C delete V that you want. But what I'm going to do is I'm going to choose a path that starts at U and I'm going to stop as soon as we hit C delete V. So what I'm going to do is if they're in the same component, I can choose a path P such that, let me just say, I'm going to go from U to some vertex in V of C delete V. And just for kicks, I'm going to choose a shortest. Right? So I mean over all paths that have the first vertex in U and the last vertex in that set of vertices that are vertices of the cycle C but not V. Over all such paths, I'm just going to choose the shortest one. Now, why have I chosen a shortest one? Just one reason. I want to start at U. I want to end up on my cycle C, but I don't want to touch the cycle C in the middle. That's annoying. If it touched the cycle C in the middle, then I have a shorter path from U to the cycle C. So that's what I'm going to do. Oh, I should have said, oh my gosh. I'm choosing a shortest path P in G delete V. So I'm choosing a shortest path in G delete V from the vertex U to the rest of the cycle. Again, I'm in the case where U and the rest of my cycle lie in the same component after deleting the vertex V. So that means there's a path that starts at U and ends at any vertex of V of C without V that I like. I can end wherever I want. But what I'm going to do is I'm going to choose a shortest path that starts at the vertex U and ends at a vertex of my cycle other than V. Or maybe it's best to say within the graph G delete V, I'm going to choose a shortest path starting at U and ending at a vertex of the cycle C, which obviously can't be V. Now, now there's a little bit to think through here, but what's going to happen is very much like the other argument that we saw before. In fact, it really is just the same. You can see I've drawn this edge F, but in fact, you're just going to use the edge F and then the path P, and it's going to act like a longer edge F, right? Wherever I go to draw this, the other end of this path P, right? One end is U, the other lies somewhere on this cycle, but not at the vertex V. And wherever you drop it down, you can always just take you can always find a cycle that uses the edges E and F. I mean, there are really just 2 cases here, right? It could kind of connect along the bottom here, and then that's no problem. You just throw out this middle segment, or it can connect at the top. But in fact, that's really even just the same under a flip. So in either case, this gives a... In fact, what I will say, and this is probably what it says in the notes, the graph C union P has a cycle containing E and F. And that completes the proof. So that was our second case. If there's a cycle containing E and F prime, then we we've got this sort of a cycle and just one little kind of hair sticking out, and we take advantage of that structure, right? So we delete the one vertex of degree 3 in that subgraph, our vertex V, and we ask, can you still get from U back to the cycle, back to what's left of the cycle? If you can, then you can find a cycle containing E and F. If you cannot, then there's going to be a one separation of the original graph now, where V is the unique vertex in the middle, and the edge F, which is UV, is say on the right, and the edge E is on the left. And right, and so that completes our proof. Now I want to kind of readily admit that we have not chosen the shortest line through this proof. This induction is done because it's instructive. We'll in fact sort of subsume this in some cleaner, kind of quicker arguments that are more sophisticated later. But I think there's a really valuable argument to see, and it's given us a very nice take-home fact. So let me, for the moment, jump back to the actual statement, and just highlight that one again. So again, it's given us a nice fact. We now have a structure theorem that tells us when our graph has a cycle through two given edges. If I give you two edges, E and F, of a graph G, either we get a nice thing, a cycle containing both edges, or there's an obvious reason why not, namely there's a separation of order at most 1, with E on the left and F on the right. Right. Okay, so now we're going to introduce a very key definition, and we are going to prove a nice theorem that gives us a few equivalent forms of that property. So the definition a graph G is two connected if it has to be connected and it also has to have the additional property that it has no cut vertex. Right, so if of course we're trying to kind of bootstrap to some higher kinds of connectivity here, and I'm just trying to get the definition in place right now. You eventually will have a more general notion of what it means for a graph to be K-connected. But just for right now, let's focus on 2. So we're trying to keep things as simple as possible while we get the ball rolling here. So what is it going to mean for a graph to be 2 connected? Well, it's got to be a connected graph. That's what we're going to insist on. And we don't want it to have a single fail point. So there's no vertex that is a cut vertex. So it's connected, and however you delete a vertex, it stays connected. Right? That's some kind of nice, robust property of a graph, and that's what we're going to be calling 2 connected, with one additional little caveat. Right now, if I keep this definition as it is, so this is not the full definition, I haven't got to the end of it yet, but if I were to keep this as the full definition, this graph would be 2 connected. Right? This is a connected graph, and it doesn't have a cut vertex. However you delete one of the vertices, well, you still are just left with one component. But we don't like this one. It's too small. and it's not an interesting example, and it violates lots of the properties that we want two connected graphs to have. So we're going to rule it out. And the way we're going to rule this out is we're going to insist that we have at least 3 vertices. So it's connected. The other property here is the number of vertices of G is at least 3. Okay, so that's what it means to be two connected. It has to be a connected graph with at least 3 vertices, and it's not allowed to have a cut vertex. So, so lots of graphs we know are two connected. If you have a complete graph, well, if you've got at least 3 vertices in it, it's certainly going to be two connected, right? Because, well, it's connected, and however you delete a vertex, you get another complete graph, so it's connected. Same if I were to give you a complete bipartite graph with at least 2 vertices on each side, that would be a two connected graph. You've got at least 3 vertices, you're connected, and if you delete a vertex, you're still a complete bipartite graph with vertices on both sides, so you're still going to be connected. Cycles of length 3 or more are also two connected graphs. So two connected, again, it's well, this is what we're aiming for. We're looking to kind of lift up to some higher concepts of connectivity, and this is a very, very sensible one. You're going to be two connected if not only are you connected, but you also have no one vertex that deleting leaves you a disconnected graph. So it's better than being connected. You're connected, and if you delete a vertex, you're still connected. And the additional property that you have at least 3 vertices. So that's what it means for a graph G to be two connected. Now let me show you a nice theorem. So we're going to be leaning on this proposition that we have up here. We've just characterized what it means for when a graph has a cycle through 2 given edges, and that's what we're going to be leaning on in the next theorem statement. So our theorem is if I give you a graph with at least 3 vertices, then the following are equivalent. G is two connected. Now, I've already promised you the graph G has at least 3 vertices. So the saying G is two, if you already know that G has at least 3 vertices, then saying it's two connected means it's connected and there's no cut vertex. Property 2, if I give you any 2 vertices, there's a cycle containing them. So for all x, y, and v, there is a cycle containing x and y. And property 3 is G has no isolated vertex. So no vertex of degree 0. And for all edges, E, F, and E, there is a cycle containing E and F. Okay. So, right, so this concept of a two connected graph, again, a graph is two connected if it is connected, has the property that it has no cut vertex, so deleting a vertex will still leave you a connected graph. So it's a little bit tougher than just a connected graph. Not only is it connected, but however you delete a vertex, it's still connected. And this additional technical assumption that you've got at least 3 vertices. So that's what it means to be two connected. But what I'm telling you is, in fact, if I gave you a graph on at least 3 vertices, saying that it has those nice connectivity properties is equivalent to saying for any 2 vertices, there's a cycle containing both. And for any 2 edges, there's a cycle containing both. Oh, and an additional assumption, no isolated vertex. So this is very nice, right? Like that definition of two connected that we gave, it certainly seems natural. So not only are you connected, but however you delete a vertex, you're still connected. And now we're seeing that it's actually equivalent to some other nice properties. It's equivalent to saying you've got a cycle through any 2 vertices, or it's equivalent to saying you've got no isolated vertex and a cycle through any 2 edges you like. And so this is a very satisfying statement, right? It's giving us some nice equivalent form of what it means for a graph to be two connected. And it's certainly a very useful one. So now I've got three things I'm trying to show they're equivalent. What we're going to do is I'm going to show that if one holds true, then 3 holds true. If 3 holds true, then 2 holds true. And if 2 holds true, then 1 holds true. And all of these implications are very, very easy. So let's do 1 implies 3. So 1 implies 3. I'm trying to show that for any 2 edges, well, I should point. So if G is 2 connected, then G certainly can't have an isolated vertex, right? That would so certainly if I promise you that 1 holds true, if my graph is 2 connected, I certainly won't have an isolated vertex. The hard thing I've got to show you is that for any 2 edges E and F, there's a cycle containing them. But the good news is, well, we just characterized that. Suppose I gave you 2 edges E and F and there's no cycle containing them. I'm just going to draw the picture. If I gave you a cycle E and F and there's, what am I saying? Suppose I gave you 2 edges E and F and there's no cycle containing them, then what you know is that you've got a 1 separation with E on the left and F on the right. That 1 separation has to be a proper 1 separation, and that means that that vertex in the middle is a cut vertex, but then the graph couldn't be 2 connected, right? So in other words, if you do not have a cycle containing the edges E and F, your graph is going to have a cut vertex, and that means that and that would mean that 1 does not hold. So in other words, what we've sort of shown here is not 3 implies not 1. I guess maybe I should have even written that. Yeah, what we really did here is we showed that not 3 implies not 1. And that does the first implication, right? So saying 1 implies 3 is exactly equivalent to saying not 3 implies not 1. If 3 does not hold, then you have this 1 separation with E or separation of order at most 1 with E on the left and F on the right, and in that case you'd be violating property 1. So so that does this first implication. And let me just try to be efficient here and draw the picture for the next one. So how about 3 implies 2? Suppose I have property 3, so I know that I have a graph with no isolated vertex, and I know that for any 2 edges E and F, there's a cycle containing both. Let's try to prove that property 2 holds true. So right now I'm doing 3 implies 2. Well, if I'm going to prove property 2, I need to show that for any 2 vertices X and Y, there's a cycle containing them. So give me a vertex X, give me a vertex Y. There they are. I've got to show you that there's a cycle containing those 2. What do I know? Well, I know my graph has no isolated vertex. That means there must be an edge E incident with X and an edge F incident with Y. And moreover, I know for any 2 edges E and F, there's a cycle containing those 2. So there must be a cycle containing these 2 edges E and F, and that's going to be a cycle containing my edges, my vertices X and Y. So in fact, this implication 3 implies 2 is very straightforward. This is written in the notes, but I'll just say it once more again, because my vertices are not isolated, I can choose an edge, say E incident with X, and an edge F incident with Y. And now my property 3 tells me that I can find a cycle through those edges E and F that will necessarily contain X and Y, and that completes my proof. So for any pair of vertices X and Y, there's a cycle containing them. So last up, we need to do, so that completes the proof of this one. Last up, I need to show you that that 2 implies 1, and in fact, what I'm going to do is show that not 2. Sorry, I'm going to do the contrapositor. I'm going to show that not 1 implies not 2. right? So in other words, I'm now going to give you give you a graph that violates condition 1. So it's not 2 connected. And I'm going to show you that this also violates property 2. So I'm giving you a graph that's not 2 connected, right? Now, there are only 2 ways our graph G can violate that property. Because I've promised you, my graph G has at least 3 vertices. So there's no spoiling things there. This graph G has at least 3 vertices. Why is it not 2 connected? Well, there are 2 possibilities. Either it's not connected or it has a cut vertex. Well, both cases are pretty easy. If G is a disconnected graph, right? If there are multiple connected components, say G is looking like this, well, you can choose a vertex X in one component, a vertex Y in another component, and there's clearly no cycle containing X and Y. You can't even find a path from X to Y. So if G was not 2 connected because it was not even connected, then I can choose X and Y in different connected components of G, and it would certainly be the case that there's no cycle containing X and Y. So in this case, property 2 does not hold. So in other words, assuming we violate condition 1, I'm showing that you also violate condition 2. And we've just checked if you violate condition 1 because your graph is not connected, then you certainly violate condition 2. The other possibility is, well, it might be that your graph violates 2 connectivity for the reason that G has a cut vertex. If V is a cut vertex of G, then you can consider the graph G delete V. Right? My graph is connected, so that means G delete V. Assuming V is a cut vertex and G is connected, then G delete V will be disconnected, and you can choose a vertex X in one component of G delete V and Y in another component of G delete V. Now, as we have done so many times in this lesson, you can put the vertex V right back. Here's what your picture looks like. Now, and now you can readily see that there's no cycle that contains the vertices X and Y. Most obviously, every path from X to Y must contain the vertex V. If every path from X to Y must contain the vertex V, then you can't have a cycle containing both X and Y, because that cycle would have 2 different paths from X to Y that are completely disjoint apart from their ends. So, in other words, if condition 1 is violated, if your graph G is not 2 connected, then your graph will have some pair of vertices with no cycle between them, so you violate 2. And that completes the proof of that one. And it's got us to a very nice point. So we now have, we have a couple things. We are now equipped with a precise structure for when a graph has a cycle containing 2 given edges. We've got a higher notion of connectivity. A graph is 2 connected. If it's connected, deleting any vertex leaves you connected, and you satisfy this technical assumption that your graph has at least 3 vertices. And we've shown that that higher notion of connectivity, this notion of 2 connectivity, it has several equivalent forms. So saying that a graph with at least 3 vertices is 2 connected is equivalent to saying that your graph has a cycle through any 2 vertices, and it's equivalent to saying that your graph has no isolated vertex and a cycle through any two edges. And and so that's got us to a very nice point, and I will stop there.